Okay. And Laurel, is your mic on? Okay. Okay, so. Okay, people, we're going to get started. So, hello, welcome to our last talk for November. And it's my pleasure to introduce Laurel Carney, who's an old friend of mine from the University of Rochester. Today, we're going to continue to offer this lecture in a hybrid format with both a virtual and live audience. Our speaker will present for about 45 minutes, and then we'll have 10, 15 minutes for questions at the end. So for the virtual audience, those of you out in Cyberland, throughout the presentation, please use the Q&A feature, not the chat, to submit questions. And we'll try to answer as many questions as possible during the Q&A. And for the live audience, you'll just raise your hand the old-fashioned way. So today we're really happy to welcome Professor Laurel Carney. Dr. Carney's academic background is in electrical engineering. After a postdoc in psychology at the University of Pennsylvania, she settled into biomedical engineering, moving from BU in Boston to Syracuse University and now to the University of Rochester. Her work focuses on the neuroscience of hearing, combining physiology in the central nervous system, behavioral and psychophysical testing, and computational modeling. Key questions include hearing in noisy environments, speech coding, and novel models for pitch. So welcome, Laurel.
Thank you.
And Josh.
Share the screen. Just share the screen.
Yeah, you got it. You're frozen. Okay. Great.
Great. I'll take my mask off. It's very exciting to be here, and thanks for the invitation and the hospitality. So far, it's been very exciting to come to a big city. Remember, there are lots of people who actually walk around. Old hat for you guys. So this was an interesting invitation because I realized that there aren't too many of the graduate students who are working on the auditory system. So I wanted to pick a topic or at least a story that would be interesting to the group at large and not just to the handful of people who might be focusing on the auditory system. And I decided to talk about the importance of digging in and questioning the things that you're taught, the things that you read. And I think this is something that's generally true. So I first used a title like this at a summer school in Europe, a bucolic setting, and it didn't resonate at all. But I thought here at Columbia, surely there's still a thread of the spirit of questioning authority. And I just read last night, there are protests going on right now involving the grad students and the graduate student union. So good luck. So what I'm going to talk about, geez, is there a way to get rid of this? I think more hide. No, probably not right. Yeah. Sorry. There we go. Thank you. Okay. There we go. Okay, great. So I'm guessing this, at least some of you are first year students, many of you are further along than that, but you're all surrounded by old ideas, the fundamentals, the things we learn, the things our advisors teach us, the textbooks. And what I hope to get across is that we just have to keep questioning those ideas, poking at them, and then reacting to the answers and not just looking the other way when the answers aren't what they're supposed to be. hopefully this will work. There we go. Got it. So what I'm going to do is introduce you to a model. I think it's pretty accessible, but it's probably one of the oldest and I would say favorite concepts in hearing science. It's now something like 80 years old. And when you start asking questions about it, you get some uncomfortable answers. And I think the trick is, I'm not the first person to ask questions and get these uncomfortable answers, but the key is to not ignore what you see when things don't agree with the old and accepted stories, but to come up with new strategies that hopefully can address those issues. And then it's a battle because it can be really hard and uncomfortable to challenge what's old and true, so to speak. So what I'll talk about is a new strategy for addressing these topics in hearing science that we refer to as a neural fluctuation model, and I'll apply it to a couple of classical models. So let's get started. So the type of model we're interested in is understanding how sounds are represented in the inner ear and then in the nervous system. And this is an old figure from Fletcher, 1940, and I'll be talking a good bit about his work. The inner ear, the shell-shaped or cochlea of the inner ear, which I'm sure I hope you've heard a lot about from Professor Olson, is represented here in a sort of a one-dimensional spiral to illustrate the couple of things you need to know about the auditory system if you're not familiar with it. Basically, due to changes in the material properties along the length of this of the cochlea, the base is most sensitive to high frequencies and the apex is most sensitive to low frequencies. And the result is a tonotopic map or a map of frequency along the inner ear. So that's what the substrate we have to work on. Along that partition, there are the sensory receptor cells, the so-called inner hair cells, which run single file along this apparatus. And each one of those is contacted by something like 10 to 20 auditory nerve fibers. Each auditory nerve fiber goes to only one hair cell. Right, so those are the basics. And what we want to know is how are sounds represented either in the inner ear or, importantly, for understanding perception, we need to know how they're represented in the neural signals that go to the brain. Okay, so when these models I'm talking about are basically how do we read out the responses of the cochlea? And in Fletcher's world, he talked about auditory patterns, which was a representation of energy versus frequency. So you'll notice the thickening along this line. This was a representation of the spectrum of the sound and sort of he envisioned that the places where there was more energy would result in a larger response, and that would surely result in a larger response of those neurons, the neurons that innervated those spots along the cochlea. And these auditory patterns would then be conveyed to the central nervous system by the auditory nerve responses. And so a key question is, what's the resolution along this, the cochlea? How detailed a representation of the spectrum would this be? And how can you estimate that? And there's, from early days, a sense that the resolution is worse, surely seems to be worse in listeners with hearing loss. So how can we estimate that for a given listener? So here's how the story goes. So this is the so-called critical band model. And just in sense of, to kind of comment on how important this is in hearing science, I would estimate that somewhere between 90 and 99% of the psychophysical literature is based on this model. It sort of starts with this representation in the inner ear. But basically, the concept is that the inner ear can be envisioned as a bank of filters. So I mentioned there's that tune structure and the tonotopic map, but it's sampled by the auditory neurons. So if you think about it as a bank of filters, and each filter then has a certain bandwidth, and that bandwidth is really determining your resolution along the frequency axis. So if you're thinking ahead, if you want to represent speech, you'd like these filters to be relatively sharp with respect to the features that they're trying to represent. So how can we estimate the bandwidth of these filters? The idea was to challenge the system with noise and detecting a narrowband signal and noise, and that should tell you something about the bandwidth of the filters. So because of that, right away we need to think, wait, these are psychophysical filters. We're estimating this property of the inner ear, maybe, using psychophysics. So we have a listener with headphones and a button, and there's a brain in there in between the ear and the fingertip. But still, they're often generally just assumed that the results of these experiments I'll describe to you are representing the inner ear. And that's one of the questions that we have to keep thinking about, is there's a lot more going on in the ear when you do a psychophysical experiment with a listener. Okay, so as we go, I'll try to bring up some of the problems with this general approach. So how are you going to do this? We're going to challenge the system to detect a signal and noise. So if this is our noise spectrum, and this is a tone, one would think that you would use the filter that's tuned to the frequency of the tone, right? That would be the smart thing to do. So the logical strategy is that the listener should use the filter tuned to the tone, because that's where the signal to noise ratio will be highest, right? Because the signal will come through this filter at the point where the gain is highest, and the noise would be attenuated as much as possible. So marching forward, it's generally assumed that the listener will only use that filter to do this task. And what we're going to do is monitor the energy or power at the filter output. So in a 2-interval task, the listener hears 2 sounds that, if they're listening for a tone, they're going to hone in on the right filter and use the energy at the output of the filter to decide where the tone was, right? So when the tone is added, here's something else, that output would have more energy. You vote for tone, that was the second interval in this case, and we're good. And then the way to estimate the bandwidth, there's a few ways that I'll describe. One is what's called the critical ratio. And it's just the ratio of the tone intensity at threshold, where the listener can just detect it, to the intensity of the noise passing through the filter. And you assume that at threshold, there's a constant ratio there related to just basically the efficiency or how good the listener is at detecting that tone against that background. And so that ratio would then be proportional to the bandwidth. So just to get a little intuition, if the filters were broader in a listener, maybe with hearing loss or in a different species, then more noise would pass through the filter, and the tone would have to be a higher level to work against that increased amount of noise, right? So anyway, that's one way you can go about estimating these filters. And Filcher went on to introduce another strategy, which is called the band widening experiment. And the results of this experiment were really key in sort of cementing this concept, I think. So if you use a very narrow band of noise and get the listener to detect the tone, you can estimate a threshold for a given bandwidth. And as you increase the band of the noise, it's going to get harder. More noise is passing through the filter, so it's harder to detect the tone. But as you can see, at some point, most of the noise that you're adding is falling outside of the filter. So at some point, the thresholds will stop increasing because you're adding noise that doesn't matter, right? So you can then estimate the bandwidth of the filter by fitting these data, and the place where the bandwidth at which the threshold stop changing is referred to as the critical bandwidth, right? So this is the data. And as I look back at this, it's in some ways shocking that this major concept, that is the way that people think about the way sounds are represented in the inner ear, is based on relatively sparse set of data. These are thresholds versus bandwidth, and lines fit to them for different frequencies. It's a little hard to see. If you just look at this, you might say, it's kind of a lot of scatter. But It's interesting to grab each frequency, which is marked by a different symbol, and connect the dots. When you do that, this is what you see. And I think you could argue it's true that things sort of flatten out at the large bandwidths. But I would argue that none of these shapes really fit the story, right? The clear breakpoint, for example, where you would say that's the bandwidth associated with that filter. In fact, the closest might be this blue line at 1 kilohertz. But then if you look even more closely, you'll notice there's only 3 points on that curve. So it is pretty hard to say that, see, this would be the critical band, right, where the 2 lines intersect for this, and there are really no data points close to that. But yet this is the paper that gets cited. This is the data set that on which this theory was developed and believed. So let's go on. People have worked on this quite a lot, but let's go on and look at some more. So De Boer, who is a prominent worker in this whole area, I think this was around the time of his thesis work, he pulled together similar thresholds from a lot of different studies. And that at 1 kilohertz, which is the blue line here, he pulled all these data together. And if you look at this, and then you look at the Fletcher model, which is the dashed line here, there's really not a clean match, I would argue. There's no break point in this data. It's just kind of a tilt to the data points. So this is an example of someone questioning this basic framework. But then what's done with this answer? And I'm paraphrasing what his description was basically, well, the critical band has to be true. But it just seems like this band widening experiment is not a good way to describe it, which I find very interesting. And it's not unusual. I think you'll find this in your own fields. There's often the textbook story, an uncomfortable result, and then, oh, well, this must be a special case. Or maybe it works for this experiment, but not for this experiment. Let's focus on the one that seems like a better fit. And I think it's important to say, no, let's look into it and try to understand what's going on in these situations where it doesn't work. So we're going to go on. There are other ways to estimate this. Let's look at some of those. But the key is that all of the thresholds that are measured end up being interpreted in the spirit of this model, this power spectrum model, which is that the tone detection is limited by the power that passes through the filter and the filter that's centered on the tone. So here's some other strategies and other problems that come up. One thing people have tried was to avoid spectral overlap, possibly strange interactions between the tone and the noise and so forth. So you could do a similar thing where you just bring the noise in or slide it out and trace out the shape of the filter by the threshold for this tone. Again, thinking in terms of the energy passing through this putative filter versus the energy in the tone. Problem with that is that the right strategy for the listener, it was quickly recognized, would be to use use a filter that's slightly displaced, so-called off-frequency listening, because there you can just shift which filter you use and improve your signal-to-noise ratio. So that didn't really pan out. Then the next strategy was to counteract that, was to stick another band of noise on the other side, and that way the listener can't move that way. So that the presumption is, well, they're stuck listening in the middle. They're going to use this one filter that we're interested in, and we'll slide the spectrum away or bring it closer to the tone and trace out the changes in threshold with the notch width. And so lots of people have done that experiment. There have been numerous papers to estimate filter shapes with all sorts of variations on the theme, asymmetrical, changing one side with respect to the other, et cetera, et cetera. But all of the thresholds are then interpreted with this very strong assumption that what matters is the power through the filter balanced against the power, so to speak, of the tone. Okay, so what's wrong with that? Well, there's really a major challenge to this idea, which comes from a lot of work in David Green's lab, and then there's a beautiful paper by Gerald Kidd, where they did detection of a tone in a roving level paradigm. So it's kind of a cool strategy. If you think the listener is using a particular aspect of the signal to do a task, make that unreliable. So if you make it totally random, then the listener should fall apart, right? And this would work in any experiment. If you really got your sights set on a particular aspect of a measurement you're making that you think is important, if you randomize it, things better get bad, right? Well, it turns out you can randomize this, and this is just an example. So you can make this overall signal much lower, make this one much higher. You can rove these over a 30 decibel range, which is a huge range. And across the two intervals the listener is hearing, things are just completely random on every trial. Doesn't bother the listener at all. Maybe a dB elevation and threshold is all that you would see. So if you make the energy unreliable and the listeners aren't affected, then the question is, are they using energy at all? If you convince yourself they're not, and I'm convinced they're not, having listened to these stimuli, then you have to, I think, go back to all of these earlier works and the notch noise story and everything else and say, all right, the filters that were derived based on these thresholds were all assuming that the listeners were using energy. If they weren't, you have to rethink things. Same thing actually happens in the condition of the notch noise. So there was a nice study where these stimuli were also roved over this huge range, and listeners in that task also are not affected. Here I'm just reminding myself that there are a lot of other settings that have been brought up that do question the general framework of the critical band. But the way the field is address them is often to think of them as special cases, and let's not get bogged down by these details. For example, okay, roving level, yeah, that's a big problem. But let's say that the level's not roving, then maybe the listener is using energy. So I think that's the wrong approach. I really don't think we completely change the way we're detecting signals depending upon what paradigm the experimenter is using. Okay, so now let's shift into physiology. So I think of myself as a physiologist, and this is part of the reason this concept has bothered me for decades now. This is sort of a classical figure of the tuning curves of auditory nerve fibers. So it's a plot of the threshold for an increased firing rate as a function of frequency for several auditory nerve fibers. Each one of them innervates a spot along the cochlea, and you can kind of tell where by the tip of the tuning curve. That would be the frequency where they're most sensitive. And as I mentioned before, those critical band results, those estimates of the filters, even though they're psychophysical experiments, they're usually interpreted as some representation of what's going on in the physiology, what's happening in the inner ear, or what would you see in the auditory nerve. So here's the hitch. I am speaking to you, and we turned up the gain to a sound level where we were pretty sure you would all hear me comfortably, which is up around here. And so one thing to keep in mind is that if sharp tuning were really important, I would speak to you at levels like this. You can hear very soft sounds if you have good hearing, but they're much harder to understand than when we turn sound up. So the sound levels where you speak in, even in quiet, where you adjust your radio and television, where you listen to music, are up here. And auditory nerve fibers respond over pretty much the entire audible frequency range at those sound levels. So that simple notion of number of spikes or energy versus frequency doesn't quite make sense in terms of thinking about representation of sounds. The fibers just don't represent sounds that way. Here's another way of looking at this. This is the discharge rate for a single auditory nerve fiber as a function of frequency for several different sound levels, so-called response area. And it's true, the responses of every auditory nerve fiber are affected by the tuning in the cochlea. And we'll talk more about that as we go. But does it make sense to think about what the fiber's response is as sort of a simple direct tune out of energy passing through the filter? And in particular here, I took one of the lines and highlighted it. This is the line at 60 decibels, which is actually on the low side of comfortable conversational sound levels. And if you glance at it, this neuron is firing quite robustly over several hundred hertz. But the critical band would be the width of this blue bar, around 150 hertz or so at this frequency. So the responses of this neuron do not square with the simple notion of it's playing a role in conveying information in that critical band. It's doing much more over a wider frequency range. And so given this sort of look again at the excitation pattern, so to speak, in the auditory nerve fibers and the roving level result, for example, as well as others, I feel like we really need to dig in and find an alternative to the energy as a representation, as the one that matters. So let's keep going. And the physiology, I feel, has taught me different ways to look at this. So as you mentioned, the problem with the auditory nerve responses is that as you get to moderate or high sound levels, they really saturate. This is another look at that. These are 3 different types of auditory nerve fibers. Most auditory nerve fibers have a low threshold, relatively small dynamic range over which their responses change, and then they saturate, which has them in the doghouse right now in our field. People say, well, they're surely not coding anything. But my mother nature would not make the maximum of the auditory nerve sort of a useless bunch of fibers. So I'm really interested in these fibers, partly because they dominate the inputs to the ascending pathway that drives perception. So what's going on here? This is conversational levels that I've highlighted here, just to give you a feeling for the fact that indeed these fibers are saturated over that range that we use. Textbooks would have you think that saturation is a bad thing, and that surely we must be avoiding it, perhaps by depending upon the low spontaneous fibers. Unfortunately, they don't really exist at low frequencies, which is a swept under the rug. But over the important range of frequencies for speech, these wide dynamic ranges don't exist. The low spontaneous fibers have small dynamic ranges. So what are we going to do? Well, I'm actually convinced now that this saturation is a good thing, and I'll try to convince you of that. What it does is it removes the confound of a change in rate over this important range of sound levels and lets us focus in on changes in other features of the responses. But in any case, given the limitations of the average rate of these fibers for coding, we've got to turn to other cues, right? So here's a single fiber response to a low frequency tone. And one thing that you can see if you stare at it for a minute is that the timing's not random. The timing of the spikes tends to synchronize with cycles of the stimulus. So that's a feature that's been focused on quite a bit. So in addition to the discharge rate as a function of the tuning of the fiber or the place along the cochlea that it innervates, the so-called excitation patterns, which, as I mentioned, those are very dependent on sound level, and they kind of flatten out and at moderate sound levels. So the alternative is to focus in on temporal fine structure, the phase locking shown here to these detailed signals. A couple of problems with that approach. One is nobody's figured out how the brain would decode this detailed temporal information. There are a couple of special cases for which it does seem to be presumably important in terms of, say, binaural sensitivity to pure tones in an anechoic environment. That's the one condition, actually, where I think it's definitely important. But it's a hot topic right now in terms of understanding hearing loss. It's been proposed that maybe the big issue for listeners with hearing loss is a loss of temporal fine structure coding. problem is in the physiology, and this is work mostly in Mike Heinz's lab at Purdue, it's not really affected much by sensory neural hearing loss. That is, the phase locking is not much affected. So that's, I think, another thing that we shouldn't sweep under the rug. It's a kind of an Achilles heel issue. So what I'm going to tell you about is an alternative, and it's the one that we're focusing on now, which is to look at neural fluctuations, and I'll tell you what I mean by that. And this is an approach that requires thinking both about the periphery, how sounds are coded in the auditory nerve, but then following that up into the brain. So here's a response of a model auditory nerve fiber to a noise waveform and to a tone and noise. And if you are to stare at this, what would you say is the biggest difference between these two responses? Everybody's asleep. Yes, the envelope. And it's kind of a big fat difference, right? This is not subtle. It's really a nice change. So it's the red line that traces the peaks, so to speak, is what we refer to as the neural fluctuations, which is well described as the envelope of the neural response. In fact, we used to call it the envelope, and we've gotten away from that terminology because that's used so often to refer to the stimulus. And I'll try to convince you that the envelope of the stimulus is very different from this. In fact, the envelope of the stimulus would be slightly flattened when you add a tone, but the envelope of the neural response is significantly flattened because of properties in the inner ear. So the average rate, which is marked by these blue lines, doesn't change in this case when you add a tone. These fibers are saturated. Energy is not really well represented. You could try to measure the phase locking, which would be the timing of these detailed peaks represented by the black lines, would be a subtle difference. And we've gone down that path. And you can't explain the psychophysical results using the temporal fine structure for tasks like detection and noise. But the changes in these fluctuations are huge. So where do they come from? It turns out it's the sensory receptor cells, the inner hair cells, have an input-output function similar to this. And when there's a tone near the neuron's CF, so near the place where the fibers are most sensitive, that will saturate the input. And you can think of this as a winner-take-all sort of nonlinearity. That is, if there is energy or a tone, something narrowband, in the fibers, near the fiber's best frequency, it'll dominate the response. It pushes it in and out of saturation on every cycle. And it doesn't matter what else is going on, that input dominates. Where does that happen? If you look at where the saturation sort of kicks in and dominates these responses, it's right in that conversational speech range. So that's cool because, for example, speech sounds, the peaks are on the high end, the valleys are on the low end. And so you get a big difference in the amount of that flattening that you would see across different frequency channels. And again, this is all happening up where the rates are flat, but from the low end to the high end of this range, there's a big difference in the quality of that envelope of the response, right? So here's another look at it. This is the response to noise, the response to a tone plus noise near threshold. And you see this flattening. And so it's interesting. This is suggesting that just the tip of the tuning curve presumably plays a big role in driving this in the healthy ear, right? So it's not the filter bandwidth, it's so to speak. It's really the tip that's dominating in terms of this phenomenon, which is referred to as capture, right? So that this tone is capturing the response or dominating it. So if you look at several channels, and this is a response to a tone and a noise again, you see that the channel nearest the tone frequency gets flattened and the other channels are fluctuating quite a bit because in those channels, there's nothing right near the tip that's dominating, and you're seeing the results of all the beating between the different frequencies that pass through those filters. Now, if we looked at the auditory nerve average rates, there's not a lot to work with. But if you just eyeball these fluctuations, we could detect the tone and know where it is in frequency. So that's sort of schematized here by this fluctuation profile. So I like this approach for a few reasons. One is that it's driven by the saturation of the inner hair cells, and their sensitivity, therefore, is very important. So anything that impairs the inner hair cells will cause problems with this cue. It also depends a lot on what we refer to as cochlear amplification, which sets the operating point of the inner hair cells. Therefore, it's very interesting to think about how this cue would be impacted by sensory neural hearing loss, which affects both the hair cell sensitivity and cochlear amplification. So even though the neurons might be responding, if you don't have the sensitive tips to the tuning curves and also the gain to put the hair cells into the right place along that nonlinear input-output curve, this cue will be impacted. So who cares? That's the next question. This is all things we're talking about at the level of the auditory nerve. But I'll show you, it gets really interesting. And in fact, it's very interesting to midbrain neurons. And auditory midbrain neurons are actually at the level along the neuraxis as retinal ganglion cells, for those of you in vision. And it was the retinal ganglion cells of the auditory system, the midbrain neurons, that taught us to start looking at this aspect of the responses. So we do recordings in the midbrain. And it's the first place along this ascending auditory pathway where there's really strong tuning or sensitivity to fluctuations in inputs. And that's a hint, right? So the envelopes of sound matter to these neurons. Well, maybe the envelopes of other signal of sounds that aren't purposefully fluctuated, but just noise, for example, or a change when you add a tone could have a big effect too. So these neurons in the midbrain, it's the inferior colliculus in the auditory system is the midbrain. They have rates that in many cases vary quite strongly, quite dramatically with the modulation frequency. So they're often tested with sinusoidally modulated sounds. So the neurons inherit a characteristic frequency from their inputs. But if you take that characteristic frequency, which would be the fine structure here, but modulate it slowly, you can find, in this case, a best modulation frequency where you get very strong responses. There is another class of neurons that's similarly suppressed, but this is showing you what we would call a band-enhanced neuron. They also increase their rate as the depth of modulation increases. So that's shown here. So if we think about those neurons as sort of reading out this pattern, then it's pretty trivial to think about how this aspect of the responses would be reflected in the central nervous system, right? This fluctuation profile is a crude representation of how those neurons would respond to these signals. Okay. Oh, so one question then is, what's the bandwidth of this cue, right? Remember, we started out talking about critical bands and thinking about them in terms of power through a filter. Well, if the fluctuation cues are what we're proposing matters, then their bandwidth becomes interesting, because the resolution of this cue for representing sound spectrum is interesting. So we'll talk a little bit about that. And I'm going to breeze through this. The simulations I'm showing you all came from these tools that are all published and available, but we've got models for auditory nerve fibers and simple models for inferior colliculus neurons that we use that have that tuning for these fluctuations. And I'm just going to use it sort of a generic set. There's all of the best modulation frequencies are 100 hertz, which is kind of generic. They're broadly tuned. That tuning is not very important. Just the fact that they're sensitive is important. So when you do look at the resolution of this cue, you actually see things that are on the order, on that thin frequency range that seems consistent with critical bands. So although at the level of the auditory nerve, we really don't have a representation of energy as a function of frequency, in the fluctuations of the fibers, I think we do. So can we predict those tone and noise responses based on this sort of response? And the short answer is, yeah, it looks good. So when we just look at threshold versus bandwidth, the band widening experiment, you get about the right bandwidth and about the right thresholds. And I'm going to breeze through these. I just want to give you the impression that the properties are right. These are tone detection thresholds across many frequencies. So there's no roll off and phase locking that affects us. That's a big problem for the temporal fine structure models. These fluctuations occur at all frequencies. So the Q works across a wide range of frequencies. This interesting hump that you see in the data and also in the model is sort of a transition between very narrow bandwidths and bandwidths where capture starts to become a more significant cue. So that's kind of nice to see that come through in the model. And we've also applied the model to this notch noise experiment with or without the roving sound level that I mentioned earlier. And you can do a good job of, the blue line is the neural fluctuation model and the black line is the data. So you can do a good job of modeling the results. And the red line would be trying to do the same thing with those auditory nerve responses. And you can see that the thresholds, when you rove the sound level and you're trying to use numbers of auditory nerve spikes, they, as you would expect, they fly up. You know, you can't model, in some cases, you can't even get a threshold here when you just use numbers of spikes. So in general, it feels like the properties of this cue are about right for addressing this general interpretation of how sounds are represented in the inner ear. But what do real neurons do? So we've limited data suggesting that IC neurons are consistent with this. This is from a recent publication of a grad student. This is a band pass neuron, and then the other class of neurons are band suppressed. For these band pass neurons, this is the modulation transfer function for the neuron. When you increase the level of a tone, and this is a tone at the neuron's best frequency. So most people would assume that when you give it more energy at its best frequency, it should fire more, but it doesn't. These neurons turn off when you increase the tone level because you're flattening the overall input to these cells. And they are excited by fluctuations. So when you remove those fluctuations, you get a reduction in their response. And similarly, the other class, they're suppressed by fluctuations. So now when you add a tone in and you suppress the fluctuations in a sense in the auditory nerve, these neurons increase their rate. So we see in general the actual IC neurons seem consistent. Okay, that just says what I said. So just a quick summary so far, and we'll probably have to stop a bit short. These neural fluctuations, I would argue, provide a lot of information to the central nervous system in a form that it really loves, right? Because these neurons are strongly excited or suppressed by these slow fluctuations. And again, saturation is a good thing now in two ways. It's the saturation of the inner hair cells that create this cue. And saturation of the auditory nerve rates they sort of normalize it. They keep changes in rate at the level of the midbrain from being impacted by energy, at least over the range of levels that we use in daily life. And therefore, they can be impacted by changes in the fluctuations. Right? If two things were going on at the same time, it would be very difficult to decode it. And I'll show, let's see, I also mentioned this that I think is a very interesting to keep an eye on hearing loss. One mantra of mine is that a good model for hearing should be affected by hearing loss, right? And a lot of models for hearing are not. So I was going to pause, but it sounds like your model is to keep going till we're done. So let's not pause. One quick, and this will probably have to be pretty quick. I'm keeping an eye on the clock. I want to talk about pitch. pitch is another big topic, classical problem in hearing science. And a big issue for pitch is resolution. Are there any musicians here? Just a few. So resolution is a big issue for pitch because the sounds with harmonics, which are most of the sounds we use in music, I think the exception would be percussion, but sounds with harmonics elicit pitch, and how close the harmonics are together in frequency plays a big role in the way they're perceived. So the things like resolved harmonics and unresolved harmonics get a lot of press. So we were talking about resolution a few minutes ago in this issue of how this cue has a very good resolution in contrast to what you see right at the auditory nerve, for example. So can we pull this into the world of pitch? Keeping in mind that now with a stimulus with many harmonics, each harmonic will tend to capture the neighborhood and flatten out those responses. So here's the textbook story of pitch. There's a lot of focus, as I mentioned, on resolution. So at low frequencies where the filters are sharp, it's believed that things are resolved. Each filter is passing a single harmonic. And so you see these beautiful tones here. And at higher frequencies where the filters are broader in the inner ear, the notion is, well, okay, these are not resolving single harmonics, so the harmonics will beat together within these filters, and you get these this beating or these interesting envelopes. That's the textbook story, and for years, decades, there have been two camps. The listener or the scientists who believe that it's all about average rate and the excitation pattern that's shown here, and those that believe, no, it's all in the temporal fine structure. And at some point, after listening to these guys fight it out, time after time after time, you want to say, time out, something's wrong. Neither one of these models is working, give it up. There has to be another alternative, another way to look at this. So that's what we're working on. Now, keep in mind that these models do not include hair cells. There's no transduction. These are linear filters, no transduction, no capture. No fluctuation profiles have been considered so far. So what if we do that? So we're going to go on and look at fluctuations in response to these stimuli. And note how narrow these filters are. Right? These filters were derived psychophysically and don't really represent the physiological filters. So if you look at the sort of the textbook approach where you line up your channels with the harmonics, you actually don't see anything terribly different from what you would expect, right? You see good phase locking in the low frequency channels. This is frequency going up, auditory nerve. But in our worldview, every one of these channels is captured, right? They're all dominated by the harmonic that's lined up with their CF. So they're very flat responses. The midbrain is not particularly interested in this response because all the inputs are flat. These neurons like fluctuations. So what if we look between the channels? And what's interesting is even down at low frequencies where the pitch theorists say, well, everything's resolved. But I think what's happening is things are captured right where they're lined up. But at the channels in between, there's beating still, right? Because you're not capturing the channels. So you get this beautiful alternation in this case between channels that are fluctuating, and therefore you get a strong response in the midbrain, and the channels that are captured give you a weak response. So whereas at the level of the auditory nerve, you get this sort of flat excitation pattern that just gets worse and worse as you increase sound level to the levels where we do best in pitch tasks, by the way. But at the level of the midbrain, you have this really strong pattern, and it's actually better shown here. Let me jump ahead. So level dependence is a big problem for all of the models based on excitation patterns. The best representation would be at very low sound levels, and after that, things start to wash out. Whereas this fluctuation profile is quite robust, it actually gets stronger at the mid to high levels. Super high levels, it starts to flatten out, which is in fact appropriate. becomes harder to interpret these complex sounds at very high sound levels. So this is just a quick citation of a study that showed that we could predict pitch discrimination thresholds using this cue. So it's the earlier figure here is sort of a qualitative illustration of the way these sounds are represented. But one question is it represented well enough to really predict what listeners do? And that's the case without going into the details there. Oops. Yeah, and what we're doing now is trying to really formalize this strategy and address a lot of different pitch studies, because the pitch has been studied for well over a century, and there's lots and lots of data out there. So we got a lot to work with, and we're sort of recycling a really beautiful theory that was really designed to take auditory nerve excitation patterns and then derive some of the properties of pitch perception. It doesn't work out very well because the auditory nerve didn't play along, but at the level of the midbrain, we've got patterns we think we can work with and then go back and re-examine these properties. This is just a quick picture of vowels, which I should zip through to give time for questions. But this approach isn't limited to these sort of laboratory sounds. If you put in real spoken vowels, you see the flattening of the responses near the peaks in the spectrum, so that we believe that this could play a real role in encoding complex sounds that are of interest. Just this alternation, in a sense, between channels that are captured and channels where you have beating. That was some support from the physiology. So let me wrap it up. So this neural fluctuation model, we believe, provides a framework for thinking about how complex sounds are coded. And I've shown examples from these different classical tasks. I think it avoids some of the pitfalls, some of the problems that come up when you dig into thinking about rate place and temporal fine structure models, as well as an alternative way to think about what is a critical band. Is it really a bandwidth associated with that capture phenomenon, the flattening of the responses, as opposed to the power that's coming through the filters? And what we're working on next is taking this one more step to thinking about timbre, which really is a bridge to getting back to the speech work. So spectral shape is one important aspect of timbre. And at the level of the auditory nerve, it's a mess. Right? It's been really muddy. People have pretty much avoided it for good reason. But at the level of the midbrain, things really tighten up for some really interesting reasons to do with the fluctuations that get set up by these sorts of stimuli. So we're doing some modeling on this and physiology, and that's our current work. And with that, I'll thank my lab mates, and this work is all sponsored by NIDCD, so thank them too. And I'm happy to take some questions.
So I think before we take questions, Alexis is going to ask me to make an announcement. Okay, and then I'll take questions. So, okay, so I just, in a second we'll have questions, but for now I just want to close by saying that in 2 weeks, we'll have our final seminar by Maribel Vasquez from Rutgers University as she presents microfluidic modeling of retinal stem cell transplantation. And remember to follow us on social media to receive the latest updates. And you can see our social media information on the slide. Oops. Yeah, there you can see it now. So now we're going to go to questions. And I think, anyway, thank you very much, Professor Carney. That was a wonderful talk. I enjoyed it very much. And so if you guys have some questions, can you raise your hand? Okay, we have one in the back, or a couple in the back.
Yeah.
I'm gonna take this.
Oh, right. For the comments in chat, I agree completely. I don't have an answer to tinnitus. One question that was in the Q&A, and the other person commented that we should remember that resting on the shoulders of giants who set up these foundational theories, and that's absolutely true.
Hi, thanks so much for your excellent talk. This is really cool. I am not super familiar, or like my electrical engineering is not great, but one thing I was curious about is I know that children who have cochlear implants often can't enjoy music because my understanding is they have basically a series of 8 to 16 bandpass filters hooked up to the brain. And so they really only are benefiting from basically the old model and not this current, more accurate model. So I guess my question is, what does this frequency profile flattening model imply for, how do we practically translate that into the electrical engineering side of how to build a better cochlear implant?
Yeah, that's a great question. And it's more than just the limited number of filter bands, I would argue. But in fact, implants use the envelope of the output of each of those 16 filters to drive the electrodes. So the goal is to convey the envelope information to the listener, but it's the stimulus envelope. The stimulus envelope that's come through these filters. And as you may have, I don't think I can get the slide back, but remembering the speech sound, at the spectral peaks, the normal auditory nerve responses are relatively flat. The envelope fluctuations are greatest at those frequencies. So what cochlear implants are delivering will be the largest envelope fluctuations in the channels where in the normal auditory nerve it should be flat. So this is something I've been trying to raise with the cochlear implant research community, that the general picture that's delivered on the CI electrodes is in some ways like an expression I use, like a photographic negative. Right? The channels that are given the largest fluctuations in the healthy ear would be the most flat, and vice versa. So I think what this story tells us is that we need to flip the representation in a sense and change which channels are used for which type of signal. That makes sense. This would really suggest a massive change.
Yeah.
The way cochlear implant signals are delivered.
That absolutely makes sense. Thank you.
So I completely agree. This was really elegant and a pleasure to listen to. I had a very similar question, but I'll just follow it up with a brief technical one, and then I actually want to ask like a philosophical question in the spirit of your talk overall. So do you think that for stimulation for like an electrical device, something analogous to a cochlear implant, you can induce fluctuations in off-target tone and it would actually improve discrimination in the tone frequency of interest?
I would say, I would hypothesize yes, but it hasn't been tested.
Yeah, that is really interesting. Okay, so for the philosophical question, you talk about questioning authority, and I think you alluded throughout to what seemed like some axioms you have, some intuition when looking at this data. And like one time you said, like your idea of Mother Nature wouldn't do this. Mm-hmm. What advice do you have for developing that intuition? If we're learning sort of what everyone else has put together as a description of the physical world, how do you go about building an intuition that isn't solely based on dogma that comes before?
Well, I think the key word is just to question, to keep asking questions. And as I mentioned, when things don't add up, don't look the other way. That's my feeling. And then another pet peeve, and that's in our field, and I'm sure it's in all of your fields, these sort of duplex models, right? So there'll be a situation where, okay, here's this approach works here, but not here. Well, for this other situation, maybe this other approach will work. And we keep adopting these duplex models where we say, aha, this one must work here and this one must work there. And I keep stepping back and saying, really, does that make sense? So that's another situation where I like to always question duplex models because something's not adding up. But I think I guess just being a cynic and crotchety, maybe that's the right approach to sort of building up an attitude of questioning. Another thing that I find in our field in general is that even though there are real problems that have been illustrated with these models, they're comfortable. It's like, I don't know, macaroni and cheese or something. People want to believe. So in David Green did, and his whole group did some fantastic work where they started doing this roving level, these tasks that really poke holes in a lot of this. And yet, when you read the introduction and the discussion of the papers, they believe in critical bands. So it's interesting to me that we'll sometimes accept something because it's comfortable and it seems important. We want to believe it, even though we're at the same time maybe questioning the very basis on which those beliefs were built up, right? So I'm not sure if I've answered your question.
Yeah,
but I
very
think-
much. Thank you.
Yeah.
I don't know if any other Q&A questions have come through. Oh, she says it's time. Okay. All right. Well, then we're going to thank our speaker one more time.
Thank you.